Good morning, everyone. It's time to get started. So my name is Frédéric Le Gol, and I'm very pleased to chair this first session on reduced order modeling. So as Frédéric said, we are going to have 5 talks in a row, and then the discussion session. I encourage everybody to ask questions during the talks and not at the very end of the session through the chat. And please indicate in your message to which talk your question refer to, in order so that we can sort the question and have a proper discussion. So we can get started with the first video, and then I pass over to the Tripus.
Hello everyone, I am going to present a novel method for automatic design of experiments. First of all, let me just give you a short introduction. We have developed a library called Twinkle, which is for performing reduced order modeling, and it is currently available on GitHub. Reduced order modeling is a technique for complex system simplification. Twinkle is based on tensor decomposition, and it can work with either full, sparse, or even unstructured data. All this means that our models are based on data, and hence we need to perform a careful design of experiment first. It is well known that the more complex the system, the higher the computational cost for solving it. It is hence desirable to select for the design of experiment the least amount of points that allow to obtain the most accurate system prediction. Although selecting the minimum data points together with the best location in the space of the experiment is not a trivial problem. And here it comes the novelty of our approach. We are going to add new points to our initial data set so that we're going to enhance the reliability of the model prediction as well as ensuring space coverage. The new points are going to be added in an automatic way using mathematical criteria. And here is how the method works. We have divided it into 6 steps for simplification. Step 1 is pretty obvious. We need to have an initial dataset that is going to be improved through the method I'm about to describe. We then define a distance function to take into account the distance between points in the dataset as well as the space coverage. Then we define a difference function. This function evaluates the impact that each single data point has on the output. We compare the system response when A, all data points, and B, all points but one, are included in the sample. The difference between the two systems' outputs is linked to the response surface gradient in the area around the removed point. The larger the difference, the more points are needed in that area to guarantee model accuracy in that region. Nevertheless, we do not want to only take into account the difference criteria, but also the distance one. In fact, we want to cover the whole experiment space. We want then to add points in regions that are as far as possible from the existing ones, and at the same time in places where bigger gradient variations occur. Therefore, we define an objective function which takes into account both distance and different functions. We hence calculate the point which is the right candidate for maximizing the objective function, and we add it to the initial dataset, which is hence updated. We then check the stopping criteria set by the user at the very beginning. It could be a limitation on the number of points and/or a tolerance on the prediction error. If the stopping criteria is not met, we keep adding new points until the criteria is finally met. We have tested our methodology against Latin hypercube sampling with 2 different functions. The first example is the Rosenbrock function. We can see that our approach improves the results obtained with standard Latin hypercube sampling. We also benchmarked our approach using a more complex function with 4 input dimensions. Also, in this case, the prediction error obtained using our approach was reduced compared to Latin hypercube sampling. To conclude, we can say that our automatic design of experiment improves space coverage and also outperforms Latin hypercube sampling, even in more complex cases. Thank you very much. If you have any questions, I will be happy to answer them.
Thank you. So our next speaker, let me try to do that. Our next speaker is Manisha Chetri on model order reduction for viscoelastic fluid flows. And again, I encourage you to ask questions during the talks. Thank you.
Hello everyone, my name is Manisha Chetri and I'm doing my PhD at École Centrale des Nantes in Institut de Calcul Intensive Laboratory under the supervision of Dr. Domenico and Dr. Luisa. Today I'm going to present on model order reduction for viscoelastic fluids. I give you a brief context on this presentation, which is to develop a reduced framework for modeling particle suspensions in non-Newtonian fluids using 3D direct numerical simulations. We know that particle suspensions has a wide range of industrial applications ranging from medical science to food, cosmetics, paint, so on. The idea is to conceptualize a problem, do numerical simulations, perform dimensionality reduction so that an output of interest can be predicted in real time. Why particle suspensions? Due to the continuous evolution of the particle position and orientation, we need to integrate at each step the particle trajectory, which requires full simulations of the flow around the particle. And if there are many particles, which is the case always, the complexity grows exponentially. Also, certain assumptions are made. For example, the problem is solved only on a representative volume, assuming that the rheological properties in this volume is statistical representation of the entire suspension. So the objective is to reduce this computational burden of repetitive full order simulations without simplifying the underlying physics. Since we are dealing with complex fluids, there are challenges involved and we need to address these challenges. For example, the governing equations form elliptic saddle point problem and the constitutive equation is hyperbolic in nature. Combining both, they are highly nonlinear. And we need to introduce some numerical treatments like Daves-Galerkin to treat the stabilization of momentum equation, which adds additional 9 degrees of freedom of velocity gradient field to velocity, pressure, and stress tensor, which adds 19 degrees of freedom per mesh node in 3D or 10 in 2D. And we can use SUPG stabilization to stabilize the constitutive equation. So overall, this makes the complex fluid problem particularly challenging to solve in real time. But we can use model order reduction techniques, which undergoes 2 steps, offline and online. In offline step, we generate snapshots by solving this high fidelity system for a set of input parameters. And then we compute basis by doing POD or for linear systems, and for nonlinear systems, we can use some hyperreduction techniques. After computing basis, we then build Rome by projecting this large scale system onto this reduced basis. And then in online step, we solve this reduced order model for any parameter in the parametric space. In order to validate this framework, we analyze the flow past the sphere benchmark problem. We then develop a hyperreduction framework for such complex fluids. The flow parameter that we have studied is the Deborah number, which lies between 0.1 to 1.5 in 10 linear steps, and store the solutions in 200 time steps, thus generating 2000 snapshots. We have some very good results using SUPG online stabilization, which is same as full order model stabilization, and using Petrov-Galerkin offline, we have same order of accuracy convergence. And with no stabilization, that is just Galerkin in the online stage, we have same order of accuracy at least up to 20 modes. With Petrov-Galerkin offline, we have a speed up of 10 times faster, but the results can be further improved by doing some hyperreduction. Hyperreduction reduces Gaussian quadrature points, and using only 1% of the total quadrature points, we have same order of accuracy. We just need to ensure that the integration weights are positive. And with using hyperreduction, we have a computational speed up of 10 to the power 4 times faster than full order model solutions at a comparable accuracy. So we can conclude by saying that the algebraic problem is greatly simplified in the reduced framework, thus removing, due to the construction of the basis, we can remove the pressure degrees of freedom because the continuity equation is automatically satisfied. We do not need Daves-Galerkin stabilization, which removes the velocity gradient degrees of freedom. And the constitutive equation can be simplified through an offline stabilization procedure instead of expensive SCPG. We have some perspectives. If in 2D the speed up is 10 to the power 4, the speed up in 3D will have a significant impact because the complexity of RB models remains same irrespective of the spatial dimension. So such models then allow us to study complex 3D rheological models, which otherwise is computationally challenging. The only challenge right now is in the sampling the input parametric space. The sample space has to be large, meaning which means we need to compute high fidelity models for each sample point. So even if it only involves offline cost, it still needs to be minimized, which is our next objective. Thank you for your attention. Have a good day.
Thank you very much. Thanks for the nice talk. I'm not going to ask for any questions, but please ask them in the chat. While you do that, I can share the program with you. And our third speaker of this session is going to be Frederick Ekre, with a joint work with Ralph Schenicke, Frederick Larsen, and Kenneth Runeson on numerical model reduction with error estimation for computational homogenization of nonlinear poroelasticity. Please.
Welcome to my presentation. Today I want to talk about numerical model reduction for computational homogenization of nonlinear poroelasticity. My name is Fredrik and I'm a PhD student at Chalmers, and this is work I've done together with my supervisors Fredrik Larsson, Kenneth Runeson and Ralph Schenicke. I want to start with a very brief introduction to the finite element squared method. This is a multi-scale method where we split the domain into a macroscopic part, as you can see to the left, and in each quadrature point we have replaced the constitutive relations with the solution of another finite element problem on the micro scale. And then we have information passed between the scales like this. And you can imagine that solving a problem like this is very costly, since we have to solve a finite element problem in each quadrature point. And this is what my research is about, to find methods of reducing the computational cost of solving the microscale problems. And in this presentation we consider nonlinear poroelasticity as the model problem. And here you can see the RVE problem on the weak format. And we try to find the displacement U and the pressure P. For constitutive relations we have used linear relations for the stress sigma and the storage phi. And the nonlinearity here comes into play in the seepage W, where you can see that the permeability depends on the volumetric strain, or the divergence of the displacement. And to reduce the cost of solving the RVE problem, we introduce these approximations for the pressure field and the displacement field. So we define PR as the approximation, and we define it using NR modes, where PA are spatial modes that we compute, and the unknowns are the time functions xi. And the idea here is that NR, the number of modes, should be much smaller than N, where N is the size of the original finite element problem. So the pressure modes are obtained using a PUD procedure, and when those are given, we solve the displacement modes from the equilibrium equation. And this means that the equilibrium equation is implicitly fulfilled. The result of introducing these approximations in the equations from the previous slide is a small system of size nr, which can be solved much more efficient than the original system of size n. But obviously these approximations introduces another error, so we are interested in estimating this. In this work, we ignore other sources of error and focus only on the error from the NMR. And I will go through the major steps that we use to define the estimator. So first we define the linearized error equation, where we define the error as the difference between the exact solution P and the reduced solution PR. Next, we define an auxiliary form, A hat, which defines a norm and also approximately bounds the linear form from below. And using the auxiliary form A hat, we define the auxiliary error representation E hat. We can now combine the error equations, and the result from this is that the norm of the auxiliary error is an approximate upper bound of the true error. And in the last step, we find an estimate for the residual, and at the bottom here you can see the final result, where we have our residual estimate EST, which is an approximate upper bound on the norm of the auxiliary error, which in turn is an approximate upper bound on the true error. And now I want to show a numerical example. To the left you can see the microstructure that we considered. It's a simple RVE with spherical inclusions of different material parameters. To the right you can see the macroscopic strain that we apply, and we consider different amplitudes corresponding to different levels of nonlinearity. And here you can see the result for low amplitude loading, so it's close to linear behavior. To the left you can see the estimated error as a function of a number of modes, and also the exact error, which is computed based on the finite element solution. And to the right you can see the effectivity index, which is a measure on the sharpness of the estimate, and in this case we overestimate the true error with a factor of 10. And here you can see the same results but for a high amplitude loading, so we are clearly in the nonlinear zone. And in this case the true error and the estimated error doesn't go down as much, but to the right you can see that the effectivity is only slightly worse. That's what I wanted to show today. Thank you for your attention.
Thank you very much. So I encourage everybody to ask questions. So I only have 1 or 2 questions until now, so there is still room for questions. And to allow you some time to type them, let me go again to the PDF with the program. Our next speaker is going to be Kiran Saga Kolepara, and he's going to talk about model order reduction of parametric mechanical problems involving contacts. So that's the last word, which is important in this talk. Please.
Hello everyone, my name is Kiran Sagar Kollepara. I would like to talk about model order reduction of contact mechanics problems. This work is part of my ongoing thesis at ICI Central Nantes and IRT Jules Verne. Let's start with the contact mechanics problem of 2 cylinders with a parameter mu, which in this case we take as the imposed displacement on the top surface. This problem can be expressed as a min-max or a saddle point problem of this energy functional. The energy functional involves 2 variables, the primal variable, which is the displacement field, and the dual variable, which is the contact pressure field. The energy functional has 2 components, the internal energy and the contact energy. Also, there are 2 inequality constraints. One is the pressure non-negativity condition, and another is the non-penetration condition between the two surfaces. When we try to solve this problem via model order reduction, we follow the standard low-rank approach, which involves the assumption that the solution lies in a low-rank subspace. Therefore, for the displacement field U, we create a compression, we compress the data using algorithms like SVD or POD and create a basis phi. However, for contact pressure, we use special algorithms like cone projection or non-negative matrix factorization to preserve the non-negative properties of the contact pressure. This results in a purely non-negative basis phi. Also, the contact pressure is defined to lie in the positive part of the subspace, which is also called as subcone of the defined by the basis psi. However, there is still the question of whether the low-rank approach is suitable or not. If we look at on the plot on the left side, we see three contact pressure curves, and all three of them have different areas where the contact pressure vanishes completely. Because of this, these three contact pressure curves are strictly linearly independent of each other. And therefore, this gives us a hint that this space might not be a low-rank space. This hypothesis is confirmed by the plot on the right side, where we see the decay of basis error with basis rank. For displacement field, this is shown in the green curve, and we see that the basis error decays very quickly. However, for the contact pressure field, shown in blue and orange curves, the decay of error is quite slow. Therefore, the hypothesis that the contact pressure is not a low-rank subspace is confirmed. We try to use sparse methods with overcomplete dictionaries to overcome this problem. An overcomplete dictionary D is simply a matrix with large number of snapshots. We try to approximate the contact pressure field lambda using a few candidates from this dictionary. Therefore, sparsity is imposed on the coefficient lambda tilde. When we try to reconstruct the errors using this kind of method, we show the errors for points outside the training set in orange color, and we see that the errors are still significant. To conclude, we learned that the low-rank approach has limitations in terms of linear inseparability of contact pressure field. This inseparability introduces errors outside the training set. Even though sparse methods with overcomplete dictionaries can be used to solve contact mechanics problems, they do not address the inseparability issues sufficiently. In future, we would like to use nonlinear subspaces and nonlinear transformations to resolve the separability issues. Thank you very much for listening.
Thank you very much for your talk. Thank you for taking the time to explain and making a clear talk. Please go ahead asking questions in the chat while we turn to the last talk of this session. And this last talk is going to be given by Alba Muixi, and she will talk about a kernel proper orthogonal decomposition for nonlinear dimensionality reduction of parametric problem. please.
My name is Alba Mushi, and in this talk, I'm going to present a kernel-proper orthogonal decomposition, KPOD, for the nonlinear dimensionality reduction of parametric problems. Consider a parametric linear system of equations coming from the discretization of some boundary value problem with matrix and vector depending on a vector of parameters mu. Note that the family of solutions lies in a manifold of dimension equal to the number of independent parameters, which is embedded in a larger dimensional space. We dimension the number of degrees of freedom in the discretization. The KPOD is classified as a posteriori reduced order model, so the first step is to compute the training set, which is a family of solutions to the problem corresponding to a sampling of the parametric space. Then we identify a subspace of lower dimension, including the training set, and finally, for additional parameters mu star, which are not in the training set, we solve the corresponding problem in the reduced space by means of a reduced basis technique. In POD, which is the most popular a posteriori reduced order model, a linear subspace is identified by doing a PCA of the training set. But in cases in which the manifold of solutions is cursed, PCA fails to identify its intrinsic dimension. The idea behind KPOD is precisely to overcome this limitation by identifying a nonlinear manifold by means of kernel PCA, KPCA. With this, we aim to obtain the lowest possible dimension for the reduced space. The main features of the resulting KPOD are the use of local spaces accounting only for neighboring snapshots to characterize a nonlinear manifold, the addition of quadratic terms into the approximation space, the choice of the kernel function in KPCA based on a priori knowledge of the solution, and the definition of an iterative algorithm in the KPCA reduced space in order to solve the reduced system. The system for a new mu star in the original space with unknown x star can be written in reduced form in terms of a new unknown z star in the reduced space, where f to the minus 1 stands for the KPCA backward mapping that sends any z in the reduced space to the corresponding x in the manifold of solutions. The reduced problem can be solved by minimizing the residual of the system, and to compute f to the minus 1 of z in the residual, we need to choose a description for the nonlinear manifold. Here, for any x in the manifold, we take a local approximation, which is based on a linear combination of neighboring snapshots plus a quadratic contribution given by their cross products. For a given z, we identify its set of neighbors, eta, and we can compute directly the weights value in this expression by imposing the original problem. So the role of z is only to define the closest neighbors, and it makes sense to explore the reduced space discretely, taking patches of neighboring snapshots. In order to do so, we propose an iterative algorithm to explore the reduced space, which is based on the Voronoi diagram of the training set. With the neighbors of an initial guess z0, we obtain a local solution z1, and we repeat the process until two consecutive solutions fall in the same Voronoi set. If this is true, even with an additional level of neighbors, we have converged, and this is the patch of neighbors that defines the solution x star in the original space that we are looking for. As a numerical example, consider the steady advection diffusion problem. We impose direct boundary conditions on the left portion of the boundary, as described by this profile that simulates a source of pollutant, and homogeneous Neumann boundary conditions on the rest of the boundary. The problem is to be solved when varying two parameters, mu, which is the vertical position of the source, and alpha, which is the inclination angle of the advection velocity. These are some representative solutions. We plot here the concentration of pollutant for two different inclinations alpha and for different positions on the source of pollutant. As a training set, we take the solutions corresponding to these 60 randomly distributed samples in the parametric space, and for the two orange stars, which are not in the training set, we plot the solutions to the problem obtained with POD on the left and with KPOD on the right. We see that POD leads to oscillations and poor accuracy, while with KPOD, the oscillations diminish and the relative errors decrease. All the details on KPOD, including a comparison with POD for a complete set of examples, can be found in the reference. The paper is submitted, but a preprint is already available at arXiv. Thanks for watching.
Thank you very much. I'd like to also thank all the speakers of the session. I know it's not easy to record oneself, and so I'm impressed by the quality of how the speakers managed on this task. So it's time to go to the discussion part of the session. And we already had a few questions in the chat. So I'm going to ask them, and so I encourage the speaker then to come up and answer and discuss the questions. So the questions are more or less in the orders of the talk. And so the first question is to Valentina by Jérôme Vickers. And the question is, how do you decide on the relative weights of the two criteria, LOOCV and distance?
Good morning, everyone. Can you hear me?
Yes, very nice.
Okay, so that's a very interesting question. A very nice one. We actually do not know how to, since we do not know the response surface of the, or let's say the manifold that we are going to explore, we do not know it a priori. So we want to do this study in order to explore it. But since we do not know how it looks like, it is hard to select some or to decide some relative weights of the two criteria. So what we have done so far is to it's kind of like a normalization of the two ones. So it will be both function will be defined between 0 and 1, so that their contribution will be kind of like detached from the manifold structure and shape. But it is true that this is kind of like it is done to work well, but we want to improve this, and we are actually thinking already about adding relative weights, but we have not done it so far, but we have been taking this into consideration. So far, as I said, we only normalize the two functions between 0 and 1, so to detach them from the shape of the manifold, because in principle, we do not know how the function looks like before performing this exploration. I am not sure this answers your question. I hope it does.
Thank you. Well, I suggest we move to a different question, and then, oops, I've got some messages. Yes, so apparently it does. Thank you very much. So we have another question for Frederick Ekre from Christopher Carlson. And the question is, what does an approximate upper bound mean, and what determines the level of approximateness?
Yes. Can I share my screen maybe to easier show?
Yes, I guess
I think
you
so.
can. Okay. You are on.
Yes. So yeah, this is from the slides for the presentation. Mm-hmm. And the step that it's approximate in this case is this bound. So what we have done for previously, we did the same thing for the linear problem, and in that case, this bound was strict. The difference now is that inside these forms we have this nonlinearity with with the permeability. So to obtain this auxiliary form A hat, we ignore that, or we consider just the linear case. So it turns out that this approximate bound here is actually a strict bound if the pressure goes to 0, and then we recover the linear case again. So for the second part of the question, how approximate this is, I guess it depends on how nonlinear the problem is. But as you can see in the results, there are other steps in the procedure which overestimates a bit more. So this seems to be, it doesn't seem to be a big problem, this approximate bound.
Okay, thank you. I have also a question on your talk. At the end, you show for the nonlinear case that there the error does not decrease that much with the number of modes.
Yeah.
So the reason comes from the fact that of this approximation, or it comes rather from the fact that the separability somehow is not so big for the nonlinear problem?
So in this case, I think, we didn't investigate the training very much to obtain the basis. So I think in this case, it's just that the basis isn't capable of reducing the residual as much in this case. So.
Okay.
Yeah.
All right. Thank you. Where is the chat? Okay, there is yet another question for you, Frederick, from Alexei Lozinski. Do I understand correctly that your POD modes are calculated for the stationary, meaning equilibrium model, but then that you use them for the time-dependent problem? And if this is the case, what is the rationale for this?
Yeah, so we're doing the training on the transient problem, and then we extract snapshots for the pressure. So, I mean, the modes are just spatial modes, but they come from training of a transient problem. And I guess maybe the confusion was when I said that we computed these modes. So since we have the first equation here, which is actually not dependent on time for the displacement. So if we know the pressure modes, we can actually use the linearity of the first equation here and simply compute these displacements both based on the pressure modes. But the pressure modes comes from a transient training problem. So.
And then if I understood well, the CA of T, which are calculated on the pressure, then you reinsert them for the displacement, right?
Yeah, yeah.
All right. Also, I encourage the people who ask questions, and then we are trying to have the discussion with the speaker. But if the answer of the speaker let you think of yet another question, or if you want to make more precise your questions, please go ahead. I think this is it for you, Frederick, at least for now. I'm moving on the chat questions, and Frederick Larson had a question to Kiran. And the question was, how do you balance the richness of reduced basis for displacement and pressure?
Yes, can you hear me?
Yes, clear.
Okay. Thank you for the question. I just want one clarification. When you mean balancing the richness, do you mean in the sense of balancing the IMSUP condition? I don't know if
can you maybe you can go if you share your screen, maybe it could be helpful. Yes, the number of DOF.
Yes, so basically in my model, the number of reduced degrees of freedom for displacement and contact pressure were exactly the same. But there is one typical, one specific aspect of this problem, that not all contact pressure modes are active all the time. So maybe I will share my screen.
Mm-hmm. Perfect.
Okay. So here, okay, so I have a basis psi for contact pressure, which basically contains a selection of snapshots from the original snapshot set, depending on which method we use. Con projection gives me snapshots. It does not compress the snapshots. Non-negative matrix factorization, it again, it does not, it transforms the basis into something different, but still the number of columns that we have in this basis somehow corresponds to the number of snapshots that we have. And therefore, and I use cone projection method, and therefore I have same number of basis vectors in phi and psi. So when we talk about the balancing aspect, I could find one reference in the literature by Hasdonk, where the IMSUB condition is balanced by adding certain columns to the displacement degrees of freedom for a mathematical for proving mathematically that IMSUB condition is satisfied. However, if we don't try to do anything, we just simply use the basis as these, the lack of IMSUB condition cannot be proven. Only pathological cases can be constructed for the lack of IMSUB condition, and these in pathological cases are somewhat extreme cases that may not lie in the parametric space that we are exploring. So in my opinion, we don't need an explicit balancing of number of degrees of freedom.
Mm-hmm. And in your slides, maybe the slide after or two slides next, I don't remember precisely. Go, yes, here.
Yes.
When on the right hand side, where when you plot the error decay, this is do you measure the error with respect to the basis, or is that like a numerical error with respect to a reference solution?
No, this is the truncation error of the basis.
Okay.
Yes.
Okay.
And
so
the point was to demonstrate the linear inseparability, okay, not the robustness of a radius model.
Okay. Okay, clear. Thank you. Moving back to the chat. Okay. Thank you very much.
Thank you.
So we've got a question to Alba from Gabriel Alonso. And the question is, which kernel are you using for the results you are showing in your presentation? And how do you choose the parameter to define it?
Okay, can you hear me? Yes?
Yes, okay, perfectly. So
in this case, we are using an ad hoc kernel, which is built for this particular problem. So we use a kind of distance between samples which is based on physical considerations of the problem. So it's important to recall that in KPOD, we are not working with just data, as probably is the usual case in KPCA, but we are solving a physical problem. So we have a priori knowledge on how our solutions look like. So in this case, we use the centroid of the solution in the outlet boundary of the domain. And this is what we do. So the idea is to define the kernel using features of the solution that we have because we are solving a physical problem. And this is done in like this because we want to identify the intrinsic dimension of the problem and to reduce the dimension of the reduced space as much as possible so that the computations are more efficient and we can obtain solutions for new parameters quickly. So I don't know if I have answered.
Yes, all clear. Thank you.
Thank you.
So we'll still have a little bit of time for the session. We'll break around 9:50, and the next session will start at 10. I have a question for Manisha Chetri, speaking about nonlinear fluid equations. And so at some point of your talk, I seem to understand that you said that the online stabilization, for instance, was more expensive than a offline stabilization. And that was not completely clear to me. Do you mean that it's less expensive because somehow you need less degrees of freedom, or it's a different reason? Hello? Ah. Okay. So Manisha just said on the chat she's not able to speak. There's an issue on the microphone. Okay. She said she's unable to unmute.
Manisha, you are co-host, so you should be able to unmute your microphone down at the left corner. No, can you say something now? Yeah, okay. Maybe it's not the correct device that is set. To the right of the microphone, you have a small arrow. There you can check which microphone it is that you have entered. Maybe you need to change the setting. We cannot hear you still. Yeah, Frederick, maybe she can answer in the chat instead.
Certainly. Yeah, of course. Of course. Thank you for helping, Jenny. Are there other questions for the speakers? No? Maybe we can wait a little bit of time for Manisha to answer. So if I understand correctly, I'm reading what Manisha wrote. If I understand correctly, you mean why my offline cost is more? Yes, Well, there seems to be a difference in the cost of stabilization, whether you do it offline or online, and this is what it was not, the reason for that was not clear to me. But maybe it's a bit too long to discuss that by chat, I don't know. In the meantime, I've got a question for Alba. For your mapping to go from the mapping F, do I understand correctly in your slides that that was the quadratic formula that you showed at the bottom of some slide, where you have
yes. Should I share my screen?
Please go ahead.
Sorry.
Yes.
Okay, so what do you mean, this formula?
Yes, this is the F that you are considering, or
No,
no? Okay.
The F is the forward mapping from KPCA that has an explicit formula, so I don't put it here. F is known, is the standard one from KPCA.
Okay.
We need this local approximation with a formula for the X to do the backward mapping. So the backward mapping is not well defined because F is not injective. So we may have different points X in the input space that go into the same point in the reduced space. So in order to have an F to the -1 that is well defined, we need to reduce the approximation into a low dimensional manifold in the input space. And this is what we do here. We take the linear approximation, which is the usual one in KPCA, but then we have found that adding some quadratic terms into this expression, adding the cross products of the snapshots in the training set, we are able to increase substantially the accuracy of the method. So this is the formula that we use, but then we take this formula for the weights and we replace the formula into the original system of equations, and we solve a linear system for the weights.
Okay. Right. Oh, that's much clearer now. Okay. Thank you. Alba, there is yet another question for you from Yanis Amouche. How the subset eta is chosen?
Okay, well, I share again. Sorry. Okay, so in order to find the subset eta of neighbors, we use this Voronoi diagram of the training set. So we have our training set in the reduced space. These black dots are the snapshots in the reduced space. And then we build a Voronoi diagram for these points in the reduced space. So then for each point, we take as its neighbors the snapshot corresponding to the cell where we have our point, plus one level of neighboring cells in the Voronoi diagram. And then we iterate using this diagram. So the set of neighbors is defined by the neighbors in the Voronoi diagram in the reduced space. This is why we need to have a reduced space with the lowest possible dimension, because the Voronoi diagram will be more efficient to compute.
All right, thank you. All right, I don't see any left questions. So I'd
Hello,
like to
can you
thank.
hear me now?
Yes.
Ah, okay, perfect. I don't know what was happening. Sorry for the inconvenience. So can I answer your question?
Please go ahead.
Yeah, so when I meant the offline stabilization like decreases our computational cost, that was because we used Petrov-Galerkin offline stabilization and not the SUPG online. But when I meant that the offline cost will be more, it's because if we take enough rich parametric space, like enough samples, we need to solve the high fidelity solver for all the input parameters, because I'm using the classical posteriori POD. And if there are error estimators to solve such complex problem, then definitely we can solve the high fidelity solver for only few set of parameters and not all the parameters in the parametric space. So in that sense, I meant that the offline cost is huge.
All right. Thank you very much.
Thank you.
I think it's time to close the session. I'd like to thank all the speakers. I'd like to thank everybody in the audience also. And so after the break, we'll start our next session at 10 o'clock. Thank you.
Thank you so much.